Hello everyone, and let's go ahead and get started with the second video of this lab, part 2, which would be RL series circuits. Let's go ahead and do this. Hopefully I can write as well as I did last time, RL series. Nice. Okay, so the lab is asking you to build this RL series circuit, and we're going to, come on, do some theoretical calculations, and we are also going to do some measurements to validate our calculations. So again, we're given R and L, and all we're doing in this case, you can just pop out the capacitor that you used in the RC series circuit and pop in the inductor. And let's go ahead and look at our solution. So everything is actually still the same. Let me just put that in there. Our input voltage is equal to 2 volts peak to peak, right, at 10 kilohertz. And the inductor is equal to, if it tells us, 10 millihenries. And of course our resistance is still 1 kilo ohms. So let's go ahead and do our solution. Again, if you strayed away from this method for solving problems, I strongly encourage you to go back to solving problems the way I showed you back last semester. Always think your problem through before you start doing any work. It'll actually help you create sort of a path for how to solve your problem. And so let's go ahead and look at our solution. The solution again is going to be looking at all the tools we have available to us, so how to solve this problem. And so we know that we have the total voltage potential, in this case, equal to the voltage potential across the resistor. And now, different from the last circuit, the voltage drop across the inductor. We also know that from our previous experiments that, oops, there it goes, that current, when we're looking at a purely RL series circuit, that current lags the applied voltage. And again, everything is always with reference to the applied voltage. And so what does that mean? If I were to draw an actual phasor diagram, let's see if I can do this here. That this would be the applied potential across the inductor. Again, the potential across the resistor is always at 0. Right? And then we'd have some total applied potential that's somewhere in between. And it's at some angle off of here? No. Let's see if you are paying attention. It's always off the resistance. So some angle off the horizontal. See if I can find it. There it is. Okay. And continuing with our solution. There I am. Okay. We have, using Ohm's law, the voltage potential is equal to I times the circuit impedance. I couldn't put circuit here, but I think that's the way your lab writes it out. And we also have the individual components, the impedance across the entire circuit being the resistance plus the imaginary capacitive reactance. I was thinking of the last circuit. I meant to say inductive reactance. And we know that we can calculate inductive reactance using the formula 2 pi times the frequency times the actual inductance. All right. And so we have everything given to us now to actually solve this problem. So let's go ahead and solve for the inductive reactance. This should be a piece of cake. You've done this for the last one of your last two labs. And it's 2 times 3.14 times the frequency, in this case is 10 kilohertz, times 10 millihenries, which is the inductance. Interesting thing here, the kilo and the milli actually cancel each other out, right? And so this, as far as prefixes goes, turns into 600, and we'll put the J component here, 628. And so I can actually write this now. I'm going to write it in two forms. Well, I'll rewrite this as, we have no real part here because there's no real resistance in the inductive reactance. 0 plus J628. And if I wanted to write this in polar notation, we would get 628 at an angle of, anybody? That's correct, 90 degrees. Okay, so here I have this for you in rectangular and polar. And this is actually kind of good to do in case you need to do addition, which is real easy to do in rectangular, or if you're going to do multiplication and division, which is much easier to do in polar notation. Okay? So where do we go from here? So we're going to add the impedance for the circuit being 1 kilo ohm, and I'm going to put 1K plus 0 for the imaginary part for the resistance, and of course the inductive part would be 0 plus J628. And I know I'm putting in a lot of small steps here, but again, I really want to make sure that you understand where all the numbers are coming from. And again, you just add like to like, and all of this is actually in ohms. Units, don't forget our units. So we have 1K plus J628, and this is in ohms across both. Okay. And now let's go ahead and convert this to polar notation. So if we want to do that, right, where Z is equal to 1K, oops, if I can save that, squared plus 628 squared, and the square root, because this is squared also, the resultant, or the magnitude, should be equal to, okay, I'm not going to write all the individual numbers out here, squared plus 628 squared, oops, square root that, we should get something in between, which gives us 1 point, not something in between, something similar to a resultant or a hypotenuse if you're looking at Pythagorean theorem, 1.18 K, or kilo ohms in this case. And if we want to find the angle, again, I'm going to put this here just in case some of you forgot how to do this. Inverse tangent of 628 over 1K, and we end up with an angle of 32 degrees. And so now we have our impedance in rectangular format, and if I knew how to put this in a different color, I would. Oh, here it is. Thin red. Nice, let's see if this works. Yeah, I'm getting better at this. And we have right here our two components, the magnitude and the direction in polar notation. And so we have, I'm going to write them both out here. 1K plus J 628 ohms, right, equivalent to 1.18K at an angle of 32. Oops. And there we go. Okay, so this will actually help you with the second part of the lab, 6.2, where we're doing the RL circuit. Again, just like we did before with the RC circuit, you have resistance, you're given the voltage, and you're going to have to calculate for current, right? Now your voltage will be at a 0 angle, so we have what, a 2 volt at an angle of 0. Convert that to rectangular format if you need to add, or keep it this way if you're going to multiply or divide. And we're using the same formula of E is equal to I times impedance. All right, so nothing has changed. The only thing is now we're working with rectangular or polar notation, and these concepts should be nowhere near difficult for any of you to actually understand. Okay? Now I'm going to go ahead and put some notes down for you for the next part of the lab, which you should be able to do. Again, I'm not going to work all of this out. This is going to be due for homework. And let me just finish this out. What were we doing here? We're solving for current. Oh, that's right. So in your lab, you're solving for current. So you're, just to give you another heads up, yeah, the current is going to be equal, just like you would Ohm's law, E over Z. And you'd have something like, or you should have this, 0 degrees over 1.18K at 32 degrees. There we go. Okay, and so I'm going to go ahead and give you some pointers now to finish the last part of the lab. Now, let's see, how can I do this? I think I can type. Let's see if I can do this here. Well, you know what? I'm just going to write because I don't know how to switch over to the typewriter or to the keyboard. And so the next part of the lab, which is your final part of the RC-RL RLC series circuit, will not be any different. Right? Don't let the fact that you have a third component on there kind of freak you out. You're going to do the same thing for each component, and then you're going to add the capacitive and the inductive reactance parts. And remember, they're going in 90 degrees in opposite directions, so the only difference is one's going to be negative, one's going to be positive, and you're going to get a resultant. So part one, and the last part, is find the total impedance, sort of like what we did here. This is just going to be a little bit more involved. Find total impedance. And just so you'll know, or so you'll remember, let me go back to black ink. Here we go. I'm talking about this circuit right here from your lab, which is 6.3. That is supposed to have been a resistor. Let's do this and this, and we do that. And then it gives you an inductor. And then we have a capacitor. Same thing here. This is our full circuit. R, L, and C. Now the good thing about this is you've already calculated the inductive and capacitive reactance in the individual circuits. So, unless something changes, unless the frequency changes, and that's actually going to change the impedance, you already have these values calculated. So one, find the total impedance. So we calculate L and C depending on the equations. Capacitive reactance 1 over 2 pi FC. Inductive reactance equal to 2 pi FL. And again, this is going to be a plus J component, right? And some value, how do I write plus J some value like this. And over here, because this is lagging, we're going to have some negative J value. And then the resistance is not lagging or leading. So we're going to have some equation for the total impedance. And I probably should have given myself some more room. Hold on. Let me do this. There we go. And there you go. So you're going to do this for each individual one. It's kind of simple when you're doing it for a series circuit, and you'll end up with some value of R. Depending on which value is bigger, I'm not going to go back to the previous two labs, but you'll just basically add likes to likes, and you'll get some kind of value for J. And then you do the same thing. There's nothing else changes here. So once you do that, you do the same thing we did before. So part 2, I'll write this in red. I can get there. Okay. There we go. Part 2. What do we do with the simple RC and RL circuit? Using the given voltage, find current through the series circuit. Alright. And remember that a current is the same across each component in a series circuit. So once you calculate current once, it's going to be the same value for R, the same value for L, and the same value for C. So you just need to do this once for a series circuit. And then we get to the last part 3. It's just the way you would in a DC circuit. Find individual voltages. Okay, my writing's getting worse. I actually was doing really well at the beginning of these lectures. Individual voltages across each component. Across R, across L, and across C. Right. And you can label those as E of R, E of L, and E of C. Now remember that the total voltage, if you want to check your answer, should be the addition of all 3 voltages. Because the conservation of energy, the law of conservation of energy, says that they have to be equal. E of L plus E of C. So again, for your homework, you are going to use the theoretical values that you're required to find for your lab. I want you to work out each one of those for part 1, for part 2, and part 3, and that is what you'll be submitting as homework, and you'll be getting a grade for that. And thank you for your time. This should be enough to help you out with the lab.